In this problem, what we're going to do is we're going to assume that we're standing on the ground. We're going to throw our apple straight up into the air. It'll have no side-to-side motion. We're just going to throw our apple straight up into the air. What we're going to do is we're going to throw our apple, let's say, with an initial velocity 10 meters per second. So we have a pretty, not too bad. We'll assume that where this is, we're going to call this where we start the throw. That'll be our origin. So x initial is equal to 0, or y initial. In this case, we'll be actually looking at y because it doesn't really. We can call it x or y. It's just our position coordinate. And what we want to know, what we're going to do is the apple will go straight up, and it will reach some maximum height up here, and then it's going to come straight back down. So the question we want to know is, this y at the top, how high up does it go? That's the first thing we want to know. The second thing is, how much time does it take to get to the top? So how much time does it take to the top? We want to know that. And we also want to know the total time. Given just this information of how fast we threw it, we should be able to find all these things. Take a look at how we can do that. And of course, what other information do we actually have? Whenever you throw something up, all right, you can see, this is tougher than it looks, you can see that what happens, when I throw the marker up, it goes up, hits a high spot, and then falls back down. And so when there's a moment, a brief moment when it's sitting at the top, where the velocity is 0. So we're going to call this v at the top, that's 0. So when you're looking, you watch the marker, it kind of goes up, stops, and comes back down. And so that brief instant at the top, the velocity equals 0. So that's like one of our hidden pieces of information. It's one of those, whenever you see a problem where you throw something straight up in the air and it comes back down, remember that this is like one of these hidden pieces of information that you get to pull out and use. They won't tell you in the problem. You're supposed to pick that piece of information out. And of course, we have our acceleration is g, which is 9.8 meters per second squared down. So starting with just this piece of information and the fact that we know gravity, we're going to be able to find all these things out because we're going to take advantage of the fact it's going to reach 0 at the top. Let's take a look at how we're going to do that. We've kind of labeled our picture. That's where we start. We put our axis in and we labeled everything we had. So the next step is we write down our equations that we have, which is v final is v initial plus a delta t. We then also have v final squared is v initial squared plus 2a delta x. And then we have, in this case, instead of x, we should be putting y because it's a different direction, but it's okay. So then we'd have y final minus y initial is equal to vi delta t plus 1/2 a delta t squared. So whenever we have these equations, we can put y in instead of x, and it doesn't make a it makes a difference only in terms of keeping track of our proper labels. But in terms of solving the equations, it doesn't make a difference for us. Well, we need to find how high up we went, and we need to find the time to the top. So the first one that we can find is find the time to the top, because we can take advantage of this top equation to do that. We can think of it as two parts. The velocity up, we can think of it as a traveling up part and a coming back down part. And the time if we think of it as us throwing the ball initially, when it reaches the top, that's like v final of part of the segment. So what we can do is we can say, okay, v at the top is equal to v initial. It's going to be minus 9.8 times our delta t, which we don't know. and v at the top is 0. So what do we get? We get negative 10. We move this over. We divide by our negative 9.8, and that's delta t. So delta t is something like, and we know that the units are right because this is a velocity which has meters per second, and we're dividing by meters per second squared. So we cancel everything off, but we have that 1 over seconds, which is seconds. So the time it takes to get to the top is 1.02 seconds. So once we know the time to the top, we could figure out the distance to the top without even knowing the time, because we could use this equation. So let's do that. So we know that if we call v final v at the top, that means that 0 squared is equal to 10 squared minus 2 times 9.8 times our change in position. And so that's y final, which is y top, minus y initial, which is 0. So what do we have when we solve this? This is 100, and we're going to move that 100 over here, so it's negative 100. And then we're going to divide by 2 times 9.8, which is negative 19.6. And then that's going to equal y at the top. And we get that y at the top is 5.1 meter. We actually, when we throw this, it's going to go up about 15 feet, just so you have an approximation. We go up, it reaches to the top is 5.1 meters. Now there's two methods of approach to getting the total time in the air. The first is we can now start and we can recalculate for our thing to come back down to reach here. So we can calculate a time for it to free fall, right? Because when it sits at the top, v is 0, and now it's just going to free fall 5.1 meters, and we can get a time to free fall that distance. So we can do that. And we can use this equation to get our time, because we know that this is y final minus y initial. So y final is in this case 0. So when we're dropping down now, we reverse this and y final is 0. This becomes v initial is 0, and y initial is now the 5.1. That's if we're going to do the free fall back down, the second part. And so what happens now is the new y, all the information at the top becomes the initial information, and then everything is flipped and becomes the new y final. So y final is now 0. Y initial is now our distance at the top, 5.1, which is our distance we're going to free fall. V initial is now v at the top, which is 0. We didn't know delta t. And we have minus the 1/2, 9.8. So I put the minus out here that would normally go at the 1.8. And we plug in, we have our delta t squared, because we don't know what it is. So we take our negative 5.1, and we're going to divide it by, half of 9.8 is 4.9. We'll divide it by negative 4.9, and that's our delta t squared. So after we take this, we're going to take the square root of the 5.1 divided by 4.9. What do we find out? Delta t is 1.02 seconds. So what we learn is whenever we throw something up, and since we didn't have to worry about air resistance, whenever you throw something up, the time up is going to be the same as the time down. And we could have solved this many different ways, but it turns out because gravity is a constant acceleration, the time up is the time down. And notice that gravity didn't change during the whole process. The acceleration is constant whenever we throw something up and it comes back down. The acceleration is the same the whole time. What changes is the velocity changes. Acceleration is constant. It's always pointing down at negative 9.8 meters per second squared. The velocity is what's changing. You start with some, it leaves your hand with some speed, it slows down, reaches 0 at the top, and then it accelerates back down. And matter of fact, if we solved for the speed when it reaches back to your hand, it's going to be For the free fall part, it'll be negative 10 meters per second. It will reach your hand at the same speed it left your hand. And this is because this is a parabolic function because of this t squared.